Section 8.3 is all about graphs of rational functions. A class period or two ago, we defined what a rational function is. Rational function is an equation or an expression that can be written as the quotient of two polynomials. So f of x is equal to p of x divided by q of x, where both p of x and q of x are polynomials. Polynomials, remember, all of the exponents need to be positive rational numbers. So something like this, I have a quadratic divided by a linear function, polynomial divided by a polynomial. If this exponent's 12 or 13 or 100, any of those would be fine, as long as all of the exponents are whole numbers. So it can be 0. X to the 0 is okay. X to the negative first would not be okay. We previously have graphed inverse variation. 6 over x minus 2 is an example of a rational function. If I have 3x to the 1/2 over 2x minus 1, this is not a polynomial, therefore I do not have a rational function this time. So inverse variation graphs, or translations of inverse variation graphs, are a specific type of rational functions, but there are other things that are also rational functions. What's different about rational functions, at least the graphs of rational functions, with everything else we've looked at, linear functions always are in the shape of a line, or quadratics always are a parabola. Now, sometimes that parabola opens up, and sometimes it opens down, and sometimes it's a skinny parabola, and sometimes it's a big old wide parabola. But if I have quadratic, I am always going to have a parabola of some sort, or a square root graph. No matter what I multiply out here, add or subtract at the end, I'm always going to get a graph that looks like this. Or it could potentially get flipped and look like that, but the general shape of the graph's always the same. Or exponential graphs, they always look the same. Sometimes they were growth, sometimes they were decay, sometimes they grow fast, sometimes they grow slower, but the shape's the same, and same with logarithmic equations. Rational functions can look like all kinds of different crazy things. We could have something that looks like this. That would be the graph of a rational function. We could have something that looks like a line, but it has a little hole, an empty space in it, or lots of other graphs as well. So instead of like identifying a slope and a y-intercept, or even just plotting points, we're going to look at the properties, the characteristics that these graphs have, and how we can identify what these characteristics are. So the first are the zeros, or the x-intercepts of the graph. Remember, I've got y equals p of x divided by q of x for a rational function. Well, zeros, x-intercepts, I plug in 0 for y. So if I divide two things and I'm going to get 0, that means that the numerator needs to be 0. It has to be 0 divided by something. So to find zeros, what we're going to do is we're going to set p of x, the numerator, equal to 0. So zeros occur when the top is 0, but not the bottom. Vertical asymptotes. Vertical asymptotes are undefined. I would get, I misspelled vertical there. How'd that happen? I didn't even underline it. V-E-R-T-I-C-A-L. Anyway, vertical asymptotes would be when the graph is undefined. I would get undefined if I divide by 0. So vertical asymptotes will occur when q of x is 0, but not p of x. We could also have holes in the graph. A hole is when the graph exists everywhere up to one y or one x value, but then it continues through that point. So I have just one undefined point there in the graph. Holes, notice, are also undefined. So the bottom needs to be 0. Holes occur when not only the bottom is 0, but the top is also 0. So if the top and the bottom are both 0, I don't have both a 0 and a vertical asymptote. I actually don't have either of those. Instead, I have a hole. Graphs often have y-intercepts, not always, but they could have y-intercepts. We find y-intercepts the same way we did with lines. We just plug in 0 for x. And then it is also possible that we have a horizontal asymptote. For a horizontal asymptote, to find it, we have 3 different rules that apply. So what we are going to do is we are going to check the degree of the numerator and the degree of the denominator. So if I have like y equals ax to the m plus other stuff over bx to the n plus other stuff. So if m is the highest power of x on the top, n is the highest power of x on the bottom. If m is bigger than n, the degree of the numerator is bigger than the degree of the denominator, then we have no horizontal asymptote. If they're equal to each other, so m and n are the same, I have x cubed, and there's no powers of x on the top or the bottom that are bigger than 3, then I divide the leading coefficients. So I do y equals a divided by b. And then finally, it's possible that the degree is bigger on the bottom than it is on the top. In that case, we do have a horizontal asymptote, and the horizontal asymptote is y equals 0. So in example 1, we are asked to state the characteristics of the rational equation. And we are given y equals x minus 5 over x minus 3. We always want to start by factoring. In this case, x minus 5, x minus 3 can't be factored. There's nothing we can do. But if we can factor them and they have a common factor on the top and the bottom, that's going to help us out. We'll take a look at one like that here shortly. First thing we are going to do is we're going to find our zeros. Zeros occur when the numerator is 0. So I'm going to take the numerator, set it equal to 0, and solve for x. I get x equals 5. A 0, an x-intercept, is a point. I list points as ordered pairs. My x value of my point is 5, and the y value of my point is 0. Next thing we are going to find are any vertical asymptotes that we have. Vertical asymptotes occur when the denominator is 0. Adding 3 to both sides gives me x equals 3. Vertical asymptotes are lines. We write lines as equations. That is the vertical line, x equals 3. In this equation, I had no common factors between the numerator and denominator. Notice also I have no values of x that show up in both the zeros and the vertical asymptotes. So this graph has no holes. We will look at one later that has a hole. To get the y-intercept, we put in 0 for x and solve for y. That would give me negative 5 divided by negative 3. Y-intercept's a point, so we list it as an ordered pair. And the horizontal asymptote, we check the degree of the top and the bottom. The degree on the top is 1. That's the highest power of x. On the bottom is also 1. If the degree in the numerator is equal to the degree in the denominator, we do y equals a divided by b, where a and b are the leading coefficients of the numerator and denominator. So we need to divide the leading coefficients, which are 1 divided by 1. My horizontal asymptote is the line y equals 1. For now, all we're going to be doing is listing out those characteristics. The characteristics will eventually help us get the graph of this equation. So the graph, I have a point at 5, 0. I have a vertical asymptote at x equals 3. I have a point at 0, 5/3. And I have a horizontal asymptote at y equals 1. So eventually we'll talk about this graph looks something like this. So listing out these characteristics is going to help us identify what the graph looks like. Example 2, same directions. List out the characteristics of y equals x plus 4 over x squared plus 7x plus 10. Y equals x plus 4 over x squared plus 7x plus 10. Start by factoring. Got x plus 4 on the top, x plus 2 times x plus 5 on the bottom. Zeros, we set the numerator equal to 0. Gives me -4. Zeros are points. We list them as ordered pairs. If I set the bottom equal to 0, I get x equals -2 and x equals -5. Those are my vertical asymptotes. Holes occur when both the top and the bottom is 0. If that's the case, you would have been able to cross something out. Like if this were x plus 5 and x plus 5, they'd cross out and we would have a hole. We have no holes. The y-intercept, if I plug in 0 for my x, I get 4 on the top and 10 on the bottom, which reduces to 2 over 5. And our horizontal asymptote, the degree on the top is 1 and on the bottom is 2. If the degree is bigger on the bottom, we do have a horizontal asymptote, and it is y equals 0. Degree on the bottom is bigger than the degree on the top, y equals 0. One more example. It says example 1, that's a lie. Example 3. Same thing, list out all the characteristics. Y equals 3x squared minus 9x minus 30 over x cubed minus x squared minus 6x. As always, start by factoring. So we're going to take a 3 out of the numerator. And an x out of the denominator. From there, we can continue factoring. The top factors to 3 times x minus 5 times x plus 2. Numbers that multiply to -6 and add up to -1 would be -3 and +2. And notice this time I've got this x plus 2 that crosses out on the top and the bottom. This time we are going to have a hole. Zeros we find the same way. We set the numerator equal to 0. We want to set the numerator after I cross out this x plus 2 equal to 0. So either 3 equals 0, which it doesn't, or x minus 5 equals 0, giving me x equals 5. So my only 0 is 5, 0. Negative 2 is not a 0 because the top would be 0 at negative 2. The bottom would also be 0 at negative 2. I can't have a 0 and a vertical asymptote at the same point. Vertical asymptotes occur when the bottom is 0, so either x is 0 or x minus 3 is 0. Because I was able to cross out that x plus 2 on the top and the bottom, x equals negative 2, so if I take x plus 2 and set it equal to 0, I get x equals negative 2. X equals negative 2 is not a 0 and a vertical asymptote. Instead, it's the x value of my hole. To get the y value of the hole, you go to the simplified version of the expression and plug in negative 2. So we're plugging it in without the x plus 2, because if I plug it in here, I just get 0 over 0. I'm plugging in negative 2 right here, so I have 3 times negative 2 minus 5 divided by negative 2 times negative 2 minus 3. I put negative 2 in for all my x's, and I'm just simplifying here. 3 times negative 7, so I've got negative 21 on the top. Here I've got negative 2 times negative 5. So again, if there is a hole, it would occur when a factor matches up on the top and the bottom, and I can cross it out. Set whatever you crossed out equal to 0. That gives us the x value of the hole. And plug that in for x into everything that's left over after you have crossed out the x plus 2's to get the y value of the hole. Everything else works the same way. The y-intercept, if I plug in 0 for x, I get negative 30 divided by 0, which is undefined. There actually is no y-intercept. The reason for that is because I have a vertical asymptote at x equals 0. The horizontal asymptote, notice the degree on the bottom is 3, on the top is 2. If it's bigger on the bottom than it is on the top, the horizontal asymptote is y equals 0. That is section 8.3 on properties of rational functions.